students. Okay, so in the last classes we discussed about the concepts of decimation, interpolation. Okay, and we have done some problems on decimation and interpolation. Okay, so now we are going to discuss about the sampling rate conversion. Sampling rate conversion, that is represented as L by M or I by D. Okay, L is represented to interpolator. M is related to decimator. Okay, that's why we can say that the sampling rate conversion L by M, or you can say it as I by D. Okay, I by D. So the question may be asked like this: explain the fractional sampling rate conversion with the time domain and frequency domain relationships. Right. So sampling rate conversion by a factor L by M can be achieved by first performing interpolation and then performing decimation by a factor M. Okay. So sampling rate conversion by a factor L by M can be achieved by first performing interpolation and then performing decimation by a factor M. Okay. Then next point is H1 of K is anti-imaging filter and H2 of K is anti-aliasing filter. So this H1 of K is related to interpolator, and H2 of K is related to decimator, right? So H1 of K is anti-imaging filter and H2 of K is anti-aliasing filter are operated at the same sampling rate. Hence, can be replaced by simple low-pass filter with the transfer function h of k. Okay, the cutoff frequency of low-pass filter is omega c, that is equal to minimum of pi by L and pi by m. Okay, so that is the procedure of sampling rate conversion. First of all, sampling rate conversion. First of all, we will performing the interpolation and then performing decimation by a factor m. Then we'll take two filters, that is anti-imaging filter and anti-aliasing filter. These two will be combined by using low pass filter. Okay, these two will be combined by using low pass filter, and its transfer function is h of k, and the cutoff frequency of low pass filter is omega c equal to minimum of pi by L and pi by m. Okay, so let d by a, see here, so let d by a be the sampling rate conversion factor, d by a decimation and interpolation. So that implies t dash by t, t dash by t equal to d by I, or f dash by f equal to I by d. Okay, I by d. Right, I by d. Okay, then f dash will become f into I by d. Okay, f into I by d. F into I by d, or t dash by t equal to 1 by I, or 1 by t dash equal to 1 by t. So 1 by t equal to f. So these will be easy to understand later. But first of all, we will see the structure of this one. Structure of this one. This is interpolator structure, and this is the decimator structure. Okay. So interpolator structure is up upsampler followed by filter. Decimator structure is filter followed by downsampler, right? So this is the frequency sampling rate converter cascading. These two are cascaded here. So this is X of n, this is F, this is interpolator upsampler. So H1 of K is the filter. So F double dash will get by multiplying I with F. F double dash equal to IF. Okay. So IF, right? So similarly, this is Y of K, this is cascaded with the decimator. H2 of K is the filter, and this is the downsampler. Okay. So F dash will obtain as I by D, I by D into F. Okay, I by D into F, I by D into F. So this is IF, IF, F double dash equal to IF. Okay, so we will get our output here. So this is the cascading frequency sampling rate converter. Okay. So first of all, these are two filters. These two filters. This is a anti-imaging filter and this is an anti-aliasing filter. These two filters will be combined so that will get H of K, that is the low pass filter. Okay. So this is the efficient way of fractional sampling rate conversion. So figure one, the fractional sampling rate conversion is achieved by increasing the sampling rate by I, and then it is decreased by D. Okay. So cascade connection of interpolator and decimator is as shown in figure one. So here H of K is the low pass filter which is obtained by combining the filters H1 of K and H2 of K. So this low pass filter is operated at IF. IF. So IF, the F double dash equal to IF. Okay. The characteristics of LPF low pass filter H of K is given by H of E power j omega star is equal to I, where mod omega dash is less than or equal to minimum of pi by d. Okay. Or pi by L or pi by m. So r is equal to 0 elsewhere, where omega double dash is equal to 2 pi f into t double dash. Right. So 2 pi f into this t double dash is t by f. Okay. So it is here f double dash equals pf, then p double dash is 1 by t double dash is I by t, right? Or p double dash is t by I. Okay. So the sampling rate f double dash is if here. Okay. Now time domain representation. How to represent this in time domain? The sequence obtained at the output of upsampler is yi of L is equal to x of L by I, where L equal to 0 plus or minus I plus or minus 2I, etc. And it is equal to 0 elsewhere. This is equation number 1. Similarly, and the sequence present at LTA filter h of k is given by y2 of k is equal to sigma L is minus infinity h of k minus L into yi of L. That is sigma L equal to minus infinity h of k minus Li into x of L. Since y of L is x of L by I. Okay. Y of L is x of L by I. Okay. That's why you can replace y of I, yi of L by x of L by I. Okay. So this is by h of k minus Li into x of L. That is equation number 2. So by downsampling the sequence y2 of k with a factor of d, we can obtain the sampling rate converted signal y of d as y of d equal to y2 of d into d, y2 of d into d. So that is y of d is equal to sigma L equal minus infinity y2 of d in the sense this is a decimator. Okay. So y of d into d, h of d into d minus Li into x of L. That is equation number 3. So by downsampling, that's why it will become this expression y of d is equal to sigma L is minus infinity h of dd t plus k by dd minus Li into x of L. This is time domain representation. Coming to the frequency domain representation, the frequency response is given by y of e power j omega is equal to 1 by d into sigma L equal to 0 to d minus 1 y2 of e power j omega dash minus 2 pi L by d. Okay, where y2 of e power j omega dash is equal to h of e power j omega double dash into e power j omega double dash into I, or y of e power j omega dash is equal to 1 by d into sigma L equal to 0 to d minus 1 h of e power j omega dash minus 2 pi L by d into e power j omega dash I minus 2 pi L by d, or it is equal to 1 by d into e power j omega dash I by d for mod omega dash is less than or equal to minimum of pi and pi d by I, or it is 0 elsewhere. So that is about the data rate conversion. Main thing is here two filters is anti-imaging filter and anti-aliasing filters are combined as a low pass filter, that is H of K. Like this, it can be converted, data rate conversion. So this is interpolator and this is decimator, right? Like this, it will be converted. These two are cascaded through the low pass filter. Okay. So next one. Draw the block diagram of a multi-stage decimator and interpolator, or draw the networks of multi-stage decimator and multi-stage interpolator. Okay, decimator and interpolator, multi-stage decimator and interpolator. Okay, see, sampling rate conversion required in most cases is I by D. In this case, I by D is rational factor. Okay, so sampling rate conversion by rational factor I by D, as shown like this. This is the low-pass filter. Just now only we discussed this. This is interpolator. X of n, F is there. So this is IF. After the interpolator, this is IF. After the H of F dash equal to IF. Okay, then it is F into I by D. Then this is Y of D. This is the sampling rate conversion block diagram. Okay, if D is an integer, here D is an integer of a system for decimating a signal, and Fs is the input sampling frequency, then the frequency of decimated signal will be Fs by D. Okay, if D is the integer factor of a system for decimating signal and Fs is the input sampling frequency, then the frequency of decimated signal will be Fs by D. Therefore, D equal to product of I, product, this is a product factor of L is 1 to L DL. Okay, so this is H of n, H of n, H of n, this is Fs, then this is decimator, this is filter, followed by decimator, we will get Y of D, single stage decimator diagram, this one is. So this is the double stage, two stage, three stage up to n stage. So it is H of n, D1, D2. See these two, D equal to pi of L equal to 1 to L DL, right? That's why these two are cascaded. These decimators are downsamplers are cascaded here, right? So this is, if it is D1, this is Fs by D1. Fs by D is nothing but the decimated. And this is the frequency of the decimated signal. If it is D1, then it is decimated frequency of decimated signal will be Fs by D1. If it is D2, it is Fs by D1 D2. If it is Dn, this is Fs by D. Okay, like this, these are all multiplied. This is a multiplication symbol, that is pi. All are product. These are multiplied. Okay, so x of n Fs h1 of n is there. Next D1 Fs by D1, like this Fs by D. Okay, this is the multi-stage decimator. Okay, multi-stage decimator. The same manner, the interpolator factor can be factorized as I equal to pi of L is 1 to L IL. Okay, so this is single stage of interpolator I followed by filter, anti-aliasing filter. Okay, so this is IFS. IFS, this is the output. Okay, so here we are increasing the stages. So this is I1 into F. If it is I2, then I1, I2 into Fs. If it is IN, IFS. Okay, so I1, this is I1 into Fs. Okay, and this is I2. This is I1, I2 into Fs. If it is I3, I1, I2, I3 into Fs. And this is last one, HL into DL, that is IFS. Okay, so this is the multi-stage interpolator. Above one is the multi-stage decimator. This is multi-stage interpolator. Okay, so that is the solution for the question. What is that question? Explain, draw the block diagram of a multi-stage decimator and interpolator, or draw the network of multi-stage decimator and multi-stage interpolators. So this is the answer. Okay, we have to take the diagram of sampling rate conversion, and then we have increasing the factors, decimator factors and interpolator factors. Okay, and taking the frequency of decimated signal, that will be Fs by D. Okay, so that will become the multi-stage decimator and interpolator like this. The next one is with the help of block diagram, explain the sampling rate conversion by a rational factor I by D. Okay, with the help of block diagram, explain the sampling rate conversion. Sampling rate conversion by a rational factor I by D. Obtain the necessary expressions. Okay, sampling rate conversion by a rational factor is I by D. So sampling rate conversion by a rational factor I by D is obtained by cascading an interpolator with a decimator. Okay, right? So the basic technique is as shown like this. So this is an interpolator followed by filter, cascaded filter followed by downsampler. So this is decimator and this is interpolator. These two are cascaded here. Okay. Right. Another for sampling rate conversion by a rational factor I by D. Here, HU of Z, this is HU of Z, this is anti-imaging filter, and HD of Z is anti-aliasing filter. Okay, anti-aliasing filter. The overall cutoff frequency of the two cascaded low-pass filter, that is HU of Z and HD of Z, is will be minimum of two cutoff frequencies, right? Minimum of two cutoff frequencies. The frequency response HU of L is given as HU of how to get the frequency of response by taking its transform, its transform. So HU of omega equal to C from minus pi by I to pi by I, or it is 0 elsewhere. And it is HU of omega. HU of omega equal to I, C equal to I scaling factor. So I from minus pi by I to plus pi by I, or it is 0 elsewhere. So here C and I both are equal. So the frequency response of HD of L and the aliasing filter is given by HD of omega is equal to 1 for minus pi by D to plus pi by D, are 0 elsewhere. So the anti-imaging filter and the anti-aliasing filters are combined into single low-pass filter. Since both the filters are operated at the same rate, that is IFX. Okay, these two are operated at the same rate IFX. So this is the operating rate, that is I into FX. So that's why these two are combined in single LPF, low-pass filter. Okay, the frequency response or the combined filter is given as h of omega equal to I, h of omega equal to I, where mod omega is less than or equal to minimum of pi by D and pi by I. Okay, or 0 elsewhere. So figure 2 shows so the basic technique. This is the figure 2 shows the basic technique for sampling rate conversion by a factor I by D when both anti-imaging filter and anti-aliasing filters are combined into single LPF, low pass filter. So these two are combined into single LPF, that is H of L. Okay, so this is the method for sampling rate conversion by a rational factor I by D. From figure 2, the output of LPF is given as omega L, or omega L equals sigma k equal to minus infinity infinity h of L minus k into V of k. Okay, h of L minus k into E of k, or Y of k, right? So it is equal to h of L minus k I into x of k. Why? Because Y of k equal to x of k by L, x of k by I. Okay, that's why we can write this as sigma k equal minus infinity infinity h of L minus k into x of k. In the above figure, y of m is the output of the downsampler. Uh, y of m is the output of downsampler and is given by y of m equal to w d m, w w d m. Okay, y of m equal sigma k equal minus infinity infinity h of md minus k into x of k. Okay, the cell is replaced by md. Okay, now relationship between x of k and y of m is from figure to v of k. V of k is the output of upsampler. This is the v of k, output of upsampler with frequency omega v. The output of the upsampler with frequency omega v is expressed as v of omega v is equal to x of omega v into I, x of omega v into I. Or the output of upsampler is passed through a low pass filter, and hence we obtain omega L with frequency omega v. So therefore, the output of low pass filter with frequency omega v is given as omega v is equal to h of omega v into v of omega v. H of omega v into v of omega v, or it is equal to I into x of omega v into I, where mod omega is less than or equal to minimum of pi by d pi by a from equations 1 and 2. That is considered as equation number 4, and it is 0 elsewhere. So the spectrum of the output sequence is given by y of omega y is equal to 1 by d into omega y by d, or y of omega y equal to 1 by d into x of omega y by d is nothing but omega of omega y by d, since input to the down sampler is omega l. Okay, so we know that omega v equal to omega y by t. So from equation number 5 will become omega y of omega y is equal to 1 by d into omega v. Why? Because omega y by d is nothing but omega v. Okay, this is equation number 7. So from equations 4 and 7 we get y of omega v is equal to 1 by d into x of omega v comma I. Okay, here mod omega v is less than or equal to minimum of pi by d and pi by I, and it is 0 elsewhere. This is equation number 8. So from equations 5 and 8 we get omega y of omega y is equal to 1 by d into I into omega y by d. Okay, that where omega mod omega by d is less than or equal to minimum of pi by d and pi by I, or it is 0 elsewhere. Okay, so the above equation can be written as y of omega y is equal to 1 by d into I omega y by d, 1 by d x of I omega y by d, for omega mod omega y is less than or equal to minimum of pi comma pi d by I. Okay, it is 0 elsewhere. Okay, this is nothing but the conversion, sampling rate conversion by a rational factor I by d and its expressions. Okay, let's explain the block diagram of the general polyphase framework for decimator interpolator. Block diagram, the general polyphase framework for decimator and interpolator. Consider HFN is the impulse response of the filter. So it's the response. So HFN is the impulse response. So it's transformed. H of z is equal to sigma n equal to 0 to infinity z transform. HFN into z power minus n. So that it will become h of 0 plus h of n into z4 minus 1 plus h of 2 into z4 minus 2 plus h of 3 into z4 minus 3, like that. Okay, h of n into z4 minus n, right? So decimation process with the downsampler is shown in figure, that is h of n filter followed by anti-aliasing filter followed by downsampler. Okay, followed by downsampler, right? So that is h of n, x of n, h of n. Here the output of this filter is y of n, and this is downsampler, and the output of this one is y of n. Consider the transfer function of FIR filter, that is h of z is equal to sigma n equal to 0 to n minus 1 h of n into z power minus n. That is equation number 1. So this is decimation by factor d. If d is the decimation factor, then h of z is represented as h of z is equal to h of 0 plus h of d into z power minus d plus h of 2d into z power minus 2d plus h of 3d into z power minus 3d plus z power minus 1 into h of 1 plus h of d plus 1 into h of d plus 1 into z power minus d plus h of 2d plus 1 into z power minus 2d plus z power minus of d minus 1 into h of d minus 1 plus h of 2d minus 1 into z power minus d, and so on. So that h of z will become sigma k equal to 0 to n minus 1 sigma d equal to 0 to infinity h of dd plus k into z power minus of dd plus k. Okay, this entire expression will be written like this: sigma k equal to 0 to n minus 1 and sigma d equal to 0 to infinity h of dd plus k into z power minus of dd plus k. Okay, so it is by interchanging the summation terms. So sigma k equal to 0 to t minus 1 x of minus k from minus k into sigma d equal 0 to infinity h of dd plus k into z power minus dd. Okay, this can be written like this. So k equal to 0 to t minus 1 z power minus k into sigma d equal to 0 to infinity h of dd plus k into z power minus dd. Right. So where ed of z is equal to, so replace this by ed of z sigma d equal to 0 to infinity h of dt plus k into z power minus d, and we replace as ed of z, ed of z. So this is e naught into z power d plus z power minus 1 into e1 of e1 into z power d plus z power minus 2 into e2 of z power d, and so on e power ed minus 1 into z power d, where e0 into z power d and e1 into z power d are polyphase components. These two are e0 into z power d plus and e1 into z power d are polyphase components. So e0 of z power d is equal to h of z at k equal to 0. Okay. Similarly, e1 of z power d is equal to h of z at k equal to 1. Similarly, e2 of z of d equal to h of z at k equal to 2. So the matrix representation of h of z is given by h of z equal to 1, z power minus 1, z power minus 2, z power minus 7 minus 3 minus 1 into e0 of z power d, e1 of z power d, e2 of z power d up to ed minus 1 into z power d. The anti-aliasing filter represented with polyphase components and its equivalent representing decimators identity is shown in figure. Okay, shown in figure like this. So sub n 1 into e0 into z power d. This is z power minus 1 into e1 of z power d. Z power minus 2 into e2 of z power minus 2. Z power minus 3 like this z power uh, e power d minus z power d minus of d minus 1 into z power d. So that all are multiplied and cascaded with a down sampler, so that we will get YRT. Okay, YRT. That implies x of n. Okay, it implies x of n the input. So this is the down sampler. So this is E0 of z. So both are equal. So we can write this as like this. So the decimator is polyphase representation. This is the decimators with polyphase representation. Next, interpolation process with upsampler is shown in the figure like this. Using interpolator also, we can do the same thing. Okay, so first of all, we'll take the single stage interpolator, that is interpolator followed by anti-imaging filter. Okay, polyphase components of interpolator filter are R0 into Z power I, R1 into Z power I, R2 into Z power I, up to Ri minus 1 into Z power I. The anti-aliasing filter represented with polyphase components and its equivalent using decimal notation like this is equivalent to this one, like the above figure. Okay, this is the interpolated polygon representation. Okay, now obtain the expression for the output y of n in terms of x of n for the multi-rate system given as follows. Okay, so this is the given problem. This is upsampler, downsampler, and this is upsampler. This is the input, this is the output. Okay, so this is x of n. This is after the upsampler x1 of n is the output of this one. This is system one. So x2 of n is output of this one. This is system two. So this 15 can be divided like this: 5 into 3. 5 into 3. Okay, this is system 3, and this is the system 4 like this. System has upsampler, system 2 has downsampler. Okay, system 1 is the upsampler, system 2 is downsampler. Similarly, system 3 is also downsampler, system 4 is upsampler. Okay, so when system 1 and system 2 are combined, then the upsampler operation of system 1 and downsampler operation of system 2 gets cancelled. Okay, when these two are combined, the upsampler operation and downsampler operation gets cancelled. So x2 of n is equal to these operations will cancel. So directly x2 of n is x of n. Okay, x2 of n is x of n. So next system 3 and system 4 are there. X of n is input of system 3. So this is here also the upsampler and downsampler operation. These two will be cancelled. So y of n will be x of n here. These two will be cancelled. So this is delta of n. Delta of n equal to 1 for n equal to 0, plus or minus 3, plus or minus 6, plus or minus 9, etc. And is 0 elsewhere. Okay. So like this we can simplify this problem. Okay. Obtain the expression for the output y of n in terms of x of n for the multi-rate system given as follows. Okay. With this, I am concluding the today's class. Tomorrow we'll see the remaining problems, implementation of sampling rate conversion. Okay. Tomorrow we'll see this one. With this, I am concluding the today's class. Thank you.